Here we have two more linear simultaneous equations. We've put them in columns again so that we can solve them by substitution. The difference here compared to the last example is that these equations are arranged in quite a different order. They're not set up as y equals mx plus c as in the previous example. So we have to do a bit of work before we can substitute across. Now again, we have lots of choices. For instance, we could make x the subject of this equation. 3x equals 8 plus 4y. Then we'd have to divide by 3. We'd get a fraction, which is a bit awkward. Or we could make y the subject. That's even more awkward. We're going to get a fraction over 4, but that negative really complicates things a lot. Over here, we have an option. We could make y the subject here. Take x off each side, so that 2y equals 6 minus x, and then divide through by 2. But again, we're left with a fraction. Now that's not an insurmountable problem, but if we can avoid fractions, we'll probably make our life a lot easier. And so for all of those reasons, I'm going to rearrange this and make x the subject. X equals 6 minus 2y. So I have a statement for x which doesn't involve a fraction, and I now am capable of substituting that statement for x into the right-hand column. 3x minus 4y equals 8. 18 minus 6y minus 4y equals 8. 18 minus 10y equals 8. Take 18 from each side. Minus 10y equals minus 10. Divide through by negative 10 to discover that y equals 1. Don't stop at this stage. It's too easy to think that you've got an answer, so you must be finished. Never forget that you must work out the x value as well. Now it's really helpful that we've rearranged this, because all of a sudden x equals, we've got a very simple calculation to do. X equals 6 minus 2y. X equals 6 minus 2 times the value of y that we've just discovered, 1. X equals 6 minus 2. X equals 4. These lines intersect at an x value of 4 and a y value of 1. Sorry, I didn't show that properly on the way down. They intersect at 4, 1.